Welcome back to the channel. Today, we're diving deep into RSTP, the Rapid Spanning Tree Protocol, defined in IEEE 802.1w. If you've ever wondered how modern networks achieve lightning-fast convergence and prevent those dreaded network loops, you're in the right place. Let's get started. So what exactly is the Rapid Spanning Tree Protocol? RSTP is an enhancement of the original 802.1d STP, designed to dramatically reduce convergence time. Let me break down the key improvements. Why was RSTP needed? The original 802.1d allows only one topology tree in an environment, regardless of the number of VLANs. This is incredibly inefficient. More importantly, convergence time, the time it takes a port to transition to forwarding, is painfully high, typically 30 to 50 seconds. How does RSTP solve this? It supports multiple topology instances per VLAN, giving you much more flexibility in your network design. And here's the game changer. Convergence is reduced to less than 10 seconds. That's a massive improvement that can prevent significant downtime in production environments. Now let's talk about RSTP port states. This is where RSTP really simplifies things compared to the original STP. RSTP ports transition through only 3 states. State 1, discarding. The switch port is enabled, but it's not forwarding any traffic to ensure that a loop is not created. This state combines the traditional's STP states of disabled, blocking, and listening into one streamlined state. State 2, learning. Here's where things get interesting. The switch port modifies the MAC address table with any network traffic it receives. The switch is still not forwarding any other network traffic besides BPDUs. It's just learning the network topology. State 3, forwarding. This is the final state for a switch port. The port forwards all network traffic and updates the MAC address table as expected. This is the normal operational state you want your ports to be in. Notice how we went from 5 states in traditional STP to just 3 in RSTP. This simplification is part of what makes RSTP so much faster. Let's dive deeper into the port roles that RSTP uses to build its topology. Root port. This connects to the root switch or an upstream switch in the spanning tree topology. There should be only one root port per VLAN on a switch. Designated ports. These ports receive and forward frames to other switches. Designated ports provide connectivity to downstream devices and switches. Again, there should be only one active designated port on a link. Alternate port. This provides alternate connectivity toward the root switch through a different switch. Think of this as your backup path. Backup port. This provides link redundancy toward the shared segment within the same collision domain, which is typically a network hub. In modern networks, this is less common but still important to understand. Let's put it all together with a direct comparison between traditional STP and RSTP. Convergence. STP is slow at 30 to 50 seconds, while RSTP is fast, typically under 1 second in optimal conditions. Port states. STP has 5 states: disabled, blocking, listening, learning, and forwarding. RSTP streamlines this to just 3: discarding, learning, and forwarding. Port roles. STP defines root, designated, and blocked ports. RSTP expands this to root, designated, alternate, and backup ports for better redundancy handling. BPDU handling. This is crucial. STP only has the root bridge originate BPDUs, while RSTP has every switch generate its own BPDUs. This distributed approach is key to faster convergence. And response to topology change? STP relies on timers with a max age and forward delay mechanism. RSTP uses a proposal agreement handshake, which is much more efficient and faster. Link types. STP doesn't specifically define link types, but RSTP recognizes point-to-point, shared, or edge links, allowing for optimized behavior. Before we see RSTP in action, let's understand the three types of ports RSTP defines for building the spanning tree topology. Edge port. This is a port at the edge of the network where hosts connect the L2 topology with one interface and cannot form a loop. These ports directly correlate to ports that have the STP port fast feature enabled. Edge ports can immediately transition to a forwarding state. Non-edge port. A port that has received a BPDU. This is any port that's connected to another switch in your topology. Point-to-point port. This is any port that connects to another RSTP switch with full duplex. Full duplex links don't permit more than 2 devices on a network segment, so determining whether a link is full duplex is the fastest way to check the feasibility of being connected to a switch. Understanding these port types is essential because RSTP treats them differently to achieve rapid convergence. Now let's see how RSTP actually builds the topology. I'll walk you through a real-world scenario with 2 switches connecting. The setup. Switches exchange handshakes with other RSTP switches to transition through the following STP states faster. They establish a bidirectional handshake across the shared link to identify the root bridge. Here's the step-by-step process. Step 1. When 2 switches connect, they verify that they are connected with a point-to-point link by checking the full duplex status. Step 2. They establish a handshake with each other to advertise a proposal, in configuration BPDUs, that their interface should be the DP for that segment. Step 3. There can be only one DP per segment, so each switch identifies whether it is the superior or inferior switch using the same logic as an 802.1D for the system identifier. From the diagram, you can see switch 1 is the superior switch to switch 2. Step 4. Switch 2 recognizes that it is inferior and marks its local port, GI101, as the RP and moves all non-edge ports to discarding state. Step 5. Switch 2 sends an agreement configuration BPDU to the root bridge, which signifies to the root bridge that synchronization is occurring on that switch. Step 6. Switch 2 moves its RP, GI101, to a forwarding state. The superior switch then moves its DP, GI102, to a forwarding state 2. The key takeaway, the inferior switch, switch 2, repeats the process for any downstream switches connected to it. This cascading synchronization is what makes RSTP so fast. Let's talk about what happens during convergence, because this is where RSTP really shines. The RSTP convergence process can occur quickly because it ages out the port information after it has not received hellos in 3 consecutive cycles. Here's the math. Using default timers, the max age would take 20 seconds with traditional STP, but RSTP requires only 6 seconds. That's more than 3 times faster. And here's the brilliant part. Thanks to the new synchronization mechanism, ports can transition from discarding to forwarding in an extremely low amount of time, often less than a second in optimal conditions. But RSTP isn't naive. If a downstream switch fails to acknowledge the proposal, the RSTP switch must default to 802.1D behaviors to prevent a forwarding loop. Safety is still the top priority, but speed is a very close second. And there you have it, a complete breakdown of RSTP, the Rapid Spanning Tree Protocol. We covered the 3-port states, the 4-port roles, how topology is built, and why RSTP is so much faster than STP. If you found this helpful, don't forget to like this video and subscribe for more networking content. Drop a comment below if you have questions about RSTP or suggestions for future topics. Thanks for watching, and I'll see you in the next video.